In this video, we are going to prove a theorem of number theory, and the theorem is if the GCD of A and P is equal to 1, where P is an odd prime, then either a to the power P minus 1 divided by 2 is congruent to 1 modulo P, or a to the power P minus 1 divided by 2 is congruent to minus 1 modulo. So we can see in this theorem P is an odd prime. Odd prime means we all know the prime numbers are 2, 3, 5, 7, but 2 is the only even prime. Uh, Otherwise, all the primes are odd. So P is not 2. It means P is not equal to. So let's see the proof. To prove this theorem, we must know Fermat-Little theorem. And what is it? If the GCD of A and P is equal to 1, then a to the power P minus 1 is congruent to 1 modulo P. So what we can do, a to the power P minus 1 divided by 2 to the whole power 2 is congruent to 1 modulo P. So we can do a to the power P minus 1 divided by 2 the whole square minus 1 is congruent to 0 modulo P. Is a square minus b square. That means P divides a to the power P minus 1 divided by 2 whole square minus 1. Since we know that if A is congruent to B modulo M, this means M divides A minus B. So we have used the same thing here. This implies P divides a to the power P minus 1 divided by 2 minus 1, and a to the power P minus 1 divided by 2 plus 1. What we have done here, we have used the formula a square minus b square is equal to a plus b, a minus a square minus b square, a plus b, a minus b. That means, so we can claim that we either P divides a to the power P minus 1 divided by 2 minus 1, or P divides a to the power P minus 1 divided by 2 plus 1. The claim is that P either divide this number or this number. P cannot divide both the numbers simultaneously. So suppose if possible P divides both the numbers. That means what we are saying here, P divides a to the power P minus 1 by 2 minus 1, and not or, P divides a to the power P minus 1 divided by 2 plus 1. So that means P divides both the numbers. So P divides the difference of these two numbers, that is a to the power P minus 1 divided by 2 plus 1 minus a to the power P minus 1 divided by 2 minus 1. This implies P divides a to the power P minus 1 divided by 2 plus 1 minus a to the power P minus 1 divided by 2 plus 1. That means we are saying that P divides 2. And since we know that P is not equal to 2 and P is a prime number, that means P start with 3. So 3 cannot divide 2, 3 cannot divide 5 cannot divide 2. That means it is not possible that P divides 2. It is possible only when P is equal to, and it is not. P is not equal to 2. It is already given in the theorem. That means P cannot divide both simultaneously. That means P divides either this number or this number. That is the theorem, right? And if GCD of A and P is equal to 1, where P is an odd prime, then either a to the power P minus 1 divided by 2 is congruent to 1 modulo P or minus 1. So the proof is very simple, and to prove this theorem, we must know the Fermat-Little theorem.